it's for later and for others also. Turn off this video. Yeah. Okay, right. So mostly what it will consist today is maybe some examples in applying a certain tool, okay, to solve problems. So this tool is called mathematical induction. Okay. Now I know that you've told me that you have not heard about this term earlier, but there's still, what could you infer from here? From the word induction, what do you think it could mean? Yes, it's a way of proving things. Yeah, a way of proof. Very general way. But what would be the general outline of what can you extrapolate from the word induction? Yes, certainly a technique. And so the technique, right. So what kind, so it would be like you would be proving a sequence of statements. Okay. What kind of things does it try to prove? Just giving a brief outline in the beginning. Okay. So we would try to prove a sequence of statements. Okay. So this is what, so the nature of the problem where you would apply induction would usually be like a sequence of statements, a sequence of statements. So, I mean, just this word sequence of statement, this phrase is pretty vague. So can you give an example of a sequence of statements, something which naturally, find the nth term? Yes, yeah, an arithmetic sequence and find the formula for the nth term, right? And so let's say that, okay, let's make it a little more, so like let's say sum of the first n terms, right? So let's say there is this following statement sk, which says that if you sum the first k terms, then so there is a formula for it. You may or may not know this. Just see if you know this formula. That is not important, but this, yeah. So if you add the, so you know this, good. So when you add the first k natural numbers, you get this thing, okay? Now you see, this is a statement which we have not proved, but this is like a sequence of statements. So a sequence of statements doesn't mean that it's a statement about sequences. It just means that we have made a statement which in which we can vary the k, right? So I mean, there is a statement, this is true for S1, S2, and so it's a not one truth, but it's a it's a sequence of truths. Okay, and you can kind of see that the nature of this sequence of statements is that let's say the 10th one depends on the 9th one. You could kind of feel that, right? That whether this statement is true for the 10th, whether S10 is true, whether the sum of 10 natural numbers is that 10 into 11 by 2, it depends on whether the sum of the first 9 natural numbers is 9 times 10 by 2, right? You could kind of build from there. Okay, so that brings us to the second feature of this. That is, first is that this is the setting which will be usually there. But the second is very generally, very roughly speaking rather, we would try to prove the nth statement using the previous statements, right? So we prove the nth statement or kth statement using the previous one. So in the beginning, the problem, simple problems, it would be like using the n minus 1th, n minus 2th, or let's say the n minus 1th only, okay? N minus 1th statement. Okay. Or rather, I should say using the truth of n minus, I mean, assuming that the n minus 1th statement is true is the right way to say it. Yeah. So that's called inductive, right? Inducing. So the nth statement is induced from the n minus 1. Okay. So it is roughly this. Now, more formally, we will see when we do it in the problems, and then the other tricks and so on will keep coming. Okay. So you have any questions so far? All right, so then let's just quickly begin with this example itself. Yeah, this simply. So maybe example number 1 is just prove that just still writing it here again. This thing is this, and here we obviously want to say that this is true for all natural numbers, right? For all n which are natural. Okay. So I have not yet described induction clearly, but let's see from what we have discussed, what we can we say. Yeah. Yes. Hi. Yes. Yeah. Just 1 second. So hi Nagesh. So little, yeah. So we're just starting this mathematical induction. So today's class will be extremely basic, okay? But so that we can be very clear about what are the steps we use in induction and so on, right? You would have seen this topic before, but we are just in the beginning we keep it like a basic thing, and then yeah. Okay. Yes. So Satya, any idea? So you were saying something? Yes, so that is the general way, but how do we say it in a more precise, yeah, how do we make it more precise? And Nagesh, if you can tell us, because this is obviously this is something that all we can show this. This is a simple statement. I know somehow we can show this, but still we want to apply induction, and it's like a first example in induction to show it clearly. Like yes, so that is very important. Base case. So S1 is true. This one is true. And what is this? This is because 1 is equal to 1 times 1 plus 1 by 2. Okay. Okay. So this is called the base case, the smallest, because we know it's a sequence of statements. So the smallest case is true. Okay. Uh-huh. Yeah. So let me expand that here. Okay. So this is what we are assuming. Yeah. And Satya, you can, so when you're not speaking, you can just turn your mic off because I can hear my own voice. Yeah. And when you speak, you just turn it on. Yeah. Okay. So we assume this and we make it clear that we are assuming this. Okay. Okay. So then what's the next thing we should do? Yes. So here we will say that yes. So we want to show that it is true for sk plus. So we want to show that the statement is true for k plus 1. Yeah. So then let's first try to show this, and after that we will say the, yeah. But let's try to show for k plus 1. Yes. Assuming this for k. So how do we do that? Right. And then we just, yes. And so this, yeah, we simplify this and we get this. So that is fine, right? And so, okay, so what have we shown? We have shown that, and it's very important to understand this clearly because there are more pitfalls than we sometimes know. There are many pitfalls in applying induction. Okay, so this example is meant to be very clear about what induction says and what it does not say. Okay, and so that we don't make mistakes in this logical error and give wrong proofs of right statements. That's usually what happens. So what we're trying to say is that sk, what we have shown is that sk implies sk plus 1. Okay, I should say sk is true, but sk usually just means, just saying sk means sk is true, but sk is true implies that sk plus 1 is true. Yeah, this is what we have shown for all k. Okay. We have not assumed anything specific about k. That is the number one thing. Okay. So from here, why is sk true? And if somebody asks you, why is sk true for all k? Anyone? What do we say? What do we quote, or what do we say to lay the final thing? Do we say that because it's true for 1 and so it's true for 2 because k equal to 1 makes then k equal to 2 also it is true, then it's true for 3? Do we say like that, or what do we exactly say? Yeah, intuitively there is nothing to say, right? That obviously we all understand it's done intuitively, right? But how do we be logically clear? Because see, this is something non-trivial if you think about it, in sense that we are proving infinitely many statements at the same time. Okay, so what do we write? Yeah, Satya, any ideas? Nagesh, please say. Okay, so see, intuitively we know that is clear. Yeah, it's because we have shown that it is true for 1, which is crucial, and since it's true for 1, it's true for 2, right? Because of this thing that we have shown is true for sk means true for sk plus 1. So then it's true for 2, then it's true for 3. But we cannot say from here that, I cannot write that because it is true for 1 and true for 2 and so it's true for all. No, I cannot say this. I have to say by the principle of mathematical induction, we are done. See, otherwise it will not be considered as a right proof. Okay. So do you guys see a subtle difference? This is not needed in like a competitive exam, but to be clear and to avoid pitfalls later. In a more intricate problems. Yeah, we need to say that because we have shown the base case, right? And because this and these two by the principle of mathematical induction, the statement is true for all k. Okay, by mathematical induction. Our intuition is on one side. Our not even intuition, just logical reasoning is on one side. But that cannot be actually proved without mathematical induction. Okay, that logical, that the sense that we have that, okay, now it should be true for all k, it should be true for all natural numbers. That is a common sense thing, but it actually cannot be, but it can be proved some circular problems, but you cannot prove it from the other axioms, let's say. Okay, roughly speaking, I'm saying, okay. So in fact, that is so desirable that we put it as an axiom, if one wants to say it, simply, and that is mathematical induction. So one has to say this, okay, by mathematical induction. So why is it true? By mathematical induction, it is true for all k. Okay, so is this okay? Like there is a subtle difference, very small difference, maybe it's trivial, but All right, so there are no questions then. Okay, fine. Yeah, all right. Okay. So then let's move on. I mean, there are several other interesting ways to prove these kind of things, which you can think about, but the point of here is to just show mathematical induction and so on. All right. Yeah. Now here is a small thing, simple thing. Um, let's say there is the following thing. Okay, there is a sequence of horses. It's a very simple thing, but let's just see. Okay, there is a sequence of horses. Okay, H1, H2, H3, sequence of horses. Okay, and I have been told, I am told that first horse is red. Okay, and I am also told that if any two consecutive horses are red, then so is the next one. Okay. Yeah. So does this imply that all horses are red? Just a very small. No. So what? Yes. Yeah, it's just that simple, right? Yeah. We don't know if the second horse is red. And so, but in mathematical induction wise, where do we fail? Uh, because, well, basically because there's no way to prove S2, right? I think that's, yeah, that's good. Yeah, it's just a trivial thing, but I remember this somebody saying this in a more interesting way that kind of looked little more true. Okay, or maybe I was being stupid that time. Anyways, okay, so okay, all these are just fun. Let's get to more actual problems. Okay, some more interesting things. Um, yeah, let's try to do this problem. Okay? So all of you, do you guys know trigonometry? Are you guys okay with trigonometry? Satya, do you know basic trigonometric identities, or I don't know the curriculum, so. Okay, so you know the basic identity, like, so you know sine x plus y is in terms of, I don't know because the curriculum, sine x plus y. Do you know what it is in terms of x and y, sine x and sine y, or like if you want to break it? Have you seen this kind of thing? You have not seen this kind of thing. All right, no problem. No, that's okay. Yeah, so if you've not seen that, then we'll do other kind of questions. Yeah, so because this we will see this later. Okay, no issues. So we'll try to do other kind of problems. Okay, so here is a interesting question that um yeah, so we would like to show the following. Okay, so if let's say that so the way I should say it, yeah, I'm trying to say it using yeah, so here is the thing. Okay, we want to say that if n divides a minus b, okay, just putting it number theoretically. Okay, if n divides a minus b, so a and b are just natural numbers. Okay, so a and b are natural numbers, and we want to say that, well, if n divides a minus b, then show that n divides p of a minus p of b. Well, what are this p and p of a and p of b? Well, p is a polynomial. Okay, where, so don't worry, if you we can do it for simple polynomials first, and that will actually be enough, you see. And let's say that P is just a polynomial. Okay, so it is polynomial with integer coefficients. So an x to the n, an minus 1 x to the n minus 1, and so on. Yeah, or better we can first try to just prove it for simple maybe 2-degree first of all, and then we can try to generalize it. This will probably not need induction because it's just for 2 degrees, but let's see. Let's try to think about this. So, and we have no other conditions on A and B. It's a very striking, it's a very good lemma on its own. We will see later. I mean, you will see on your own when you do other problems. So you could just, this has basically, this will not need induction because this is 2 degree, but when we'll do the n degree, then maybe we will need induction. So any ideas? So just try to write it down. Just write out PA minus PB and try to, show that A minus B factorizes out. That's a natural way in which it would divide, right? So today maybe we'll focus on these number type of examples in the sense of maybe sum of series and divisibility, these two. But soon we will go into proving combinatorial facts and many, all kinds of facts, geometrical facts. Yeah, examples and many, we'll see many variants and so on. So why don't we just write it out, right? It should come. How hard can it be? Just 2 degree. So just write this down. So we write this a square plus a1a plus a naught, right? And then we write, yes, am I right? Nagesh and Satya, is this like natural, right? Just to, yeah, just to write out what it, so from here, what should we do to show that n divides this, I mean, n divides this expression? What is a natural thing to, looking at this expression, what's the most obvious thing to do? Yes, a naught gets cancelled. Yes, right. So we take a1 and we do a minus b. Ha, nice. Okay. So we have got the non-inductive part of the problem. So that's why it's good to do the 2-variable case, I realize. It means now we understand the non-inductive part. And so this is fine. And so, I mean, it had to be like this, right? Because nothing was given about a minus b, right? So better we show that this is a multiple of a minus b. Nothing more was given, right? So Satya, is this example okay? Yeah. So this is just a simple thing. And even you can imagine that for 3 degrees, you can do the same thing. Okay. But now if we want to change this to n degree, then what do we have to do? Or let's say 5 degree. Yeah. And now you would know what you want to happen. I mean, what divisibility you want to have, because we have done the 2-degree case and dot dot dot. Yes. And this will be a very central example in many things in number theory and even later. I mean, other topics. So, well, we just write out same things, right? You just see, the whole point here is that when you write out this, you get this kind of thing, right? A to the 5 minus b to the 5. And similarly, it goes on. But really, I mean, it should be clear that we basically want to say that this is divisible by a minus b. Right? I mean, it has to happen like that, isn't it? And this is divisible by a minus b, which you can show by factorization. And earlier ones is standard factorization. Yeah, is it fine, Nagesh? That's a natural thing that you would want to prove now. Right. Yeah. So we want to, right. So we want to show, and then we'll be done, obviously. We want to show that a minus b divides this. Yeah. But do any one of you know how to show such a thing? And in general, obviously, we would want to show, and that's a statement that we have to show, is for any k, or for any n, but let me not use n here. For any k, this is the statement we want to show. So you can try doing it for a to the 5, or you can try to think about this a to the k minus b to the k thing in general. For all k. And it might actually be easier to prove it for all k. You may see some pattern and then you may apply some kind of induction than to prove it for 5, or let's say to prove it for 100 separately. So which one should we? So do anyone of you know how to do it for the 5 keys? Because that's something like either you know or you don't know. It's a little because I mean, yeah, one can still think of, but how to show that a to the power of 5 minus b to the power of 5 is divisible by a minus b? So this difference of powers, difference of same powers, is divisible by the base. So okay, so you guys have not seen this thing, this kind of thing. Even in the polynomial class, Satya, have you seen this kind of thing in the polynomial chapter? Because usually they would like ask you maybe like in this form. Have you seen? Can you think? Yeah, but can you think of? We can all think of this kind of question? Can we apply somehow the theory of polynomials? Like this is a polynomial px. We want to say that what am I asking? I'm asking, is x minus 1 a factor? That's the same thing, right? Is x minus 1 a factor? That's all I'm asking. So by the remainder factor. Yeah, certainly long division you can certainly use. That's right. That's correct. But also there is this thing called the remainder factor theorem or something like that. It's the remainder factor theorem, right? Which is basically saying that, I mean, if x minus 1 is a factor, then the remainder at 1 is 0. Right. But let me say it in a way that's better, I think, is that basically we say, okay, let's see what happens. We apply division as using long division, but we only apply it at one step. We don't apply it explicitly. We apply a division in the sense that we get a quotient and we get a remainder. The remainder will be a number, right? Because it's going to be a constant. Yeah, degree will be less than 1. It's a constant thing. Let's say some c, right? How do you find this c? Well, you just put x equal to 1. There's nothing else to do, right? Let's put x equal to 1 because this will go away and the c is 0. And so the c is 0. The c has to be 0. Right? There's unique remainder. C is 0. But what does this mean? This means this. And this means that x minus 1 is indeed divisible by x to the power 5 minus 1. So just see if this point is okay. Smaller numbers in the sense of smaller in the powers. Oh, oh that's right. Yes. So then, but then, so why do we want to see it for other values of a and b? That's yes. So I mean, so if you see it for different numbers, different values of a and b, that would maybe help you to understand the statement is true, right? But that itself may not help you to guess the proof or understand the proof, right? Because how I see it is that the nature of the statement is that, I mean, this 5, if you can prove it for a to the 4 minus b to the 4 and a to the 3 minus b to the 3, you could combine those things to prove it for a to the 5 minus b to the 5 for any a and b. You see, right? That is the nature of the statement. But changing the values of a and b and doing, I don't know if you can still do it, but with messy, but it could probably be done. Yeah. But then what we have done here is a little special case in a sense, but it's a remarkable application of polynomials, right? But if you have taken b equal to 1, that's okay. That no one worries about that. One can adjust the proof to that also. But we have taken b equal to 1, for example, right? But we have shown that for any x, it works. So Nagesh, is this okay? Yeah, Satya and you also. This remainder, this technique. Right. Yeah. And basically, you can just say this by this only. One doesn't even need to quote the remainder factor theorem or such thing. But I mean, in the sense that same thing. Yeah. So my point here is that now you can prove, using this, you can prove it for any n. Right. Yeah. But the point here is that once we have shown this, when we have shown this is 0, it means that for any x this is true. So we can put x equal to anything and we are done. Okay, but that will be going in a different direction. We don't want to apply polynomial theory to do this problem. We want to do it by induction. Okay, so let's go by induction. Basically, there we just said that everything, x to the power 5 minus 1, you could divide by x minus 1 and you can check that the remainder is 0. But we found the remainder without finding the quotient. Okay, so that is what it was. So this is basically done. In more or less, right? You can now imagine how to prove this. You can let's say, okay, so let's say that if I told you, assume, yeah, let's do this one. Assume this. Can you assume this to prove this? So this is again not induction, but just asking. So if you assume that this x minus 1 divides x to the power 5 minus 1, that basically just says that for every x, it's true. Yeah, if you assume that statement, which we have proved already, now can we prove that A minus B thing? That for any A and any B, the above thing holds. So let's think, right? Okay, so think about this for homework. Think about this one for homework, right? So it's a very the thing is that it's like a statement which we are showing for where the other variable is one, and then we want to show it when the other variable is not one, right? So this is like this is like a normalization of the statement, like dividing by b or something you have to do. But think about it, and this seems correct, but how do you show it? Just yeah, but this is not our goal currently. So we will let's move. Yeah. Yeah. But let's discard this a minus this thing, and we try to show this in general. Yeah. Because you see, we have the base case. If we know that, I mean, we know that a minus b divides a minus b. In fact, we also know a minus b divides a square minus b square, and so on, right? Even for 3, we know. How do we show this? So let's say that you can assume, I mean, you will have to, right? You have to assume, let's say, for k minus 1, right? See, that's again the point of induction, right? You assume for some k minus 1 and you prove for k. Or you assume for k and prove for k plus 1. That's, yeah. Assume that this is true. Can we use this to prove the statement? Somehow, some manipulation. Yeah, just think I'll plug in the charger. Yeah. See, the whole thing is that could you write this thing in terms of this thing somehow, right? Then you could convert this, or from this can be built to this. Yes, we have to do something like that. Either you go from below to the above one or to the k case, or from k to k minus 1 also. If you go, then we can maybe work backwards. So basically, can we go from one to the other somehow, some connection? Let's imagine, yeah, let's see, there may be several ways to do this, right? But given this, what can I do? I can certainly multiply by a. This will certainly be true, right? No doubt. Yeah, certainly be true. But why am I doing this? To bring in a to the power k. You could do it in other ways, but Just to bring in a to the power k, go to get this kind of statement, I'm multiplying by a, right? So what is this? This is just a to the k minus b to the k a. Yeah. But then what should I do next? I need a b to the k also, right? So this manipulation is okay, right? I'm just multiplying by something to make it as somewhat close to what the statement that I need. Right? Somehow bringing in a to the k. Now these are not very interesting ways to do these problems as far as understanding the nature of divisibility and so on is concerned. There are better ways to do this, but we are learning the technique of induction. Yeah. Well, I mean, you want b also, so the obvious thing is to just multiply, do the same thing. Yes, yes. Yeah, any ideas? Multiply by b, right? Yes, because that's the natural thing to do next. It may not work, but we have to just try and see. So now we have this and this. So naturally, we add these two, right? We have this, and you want to add. Now you can do these things, right? If something divides, you can divide the sum also, right? It divides the sum. So we can add these two things. Just add them. And what do we? Let's see what do we get. We certainly have what we need, but we also have a little more, which may be a problem. We'll see. Now, what do you do? So this is true. This we know is true. But from here, we need to conclude that we want to show that a minus b divides a to the k minus b to the k. That is what we want to show. So I'm removing these polynomials because if the problem has reduced to this, this is what we have. This is what we need to show. Well, so it is just enough to show that the other part is divisible, right? It's in fact equivalent to show, right? It is equivalent to showing that the other part is divisible by a to the power k minus b to the power, by a minus b. You guys agree, right? If I can show that this is divisible by a minus b, whole thing is divisible by a minus b, so the difference is also divisible by a minus b, right? What else, right? So why is this true? Yes. But why is this true? Think. Okay, yeah. So if we take AB common, right. So so it becomes this. Okay. So, but this is not exactly what we assumed. But now we realize that we should also assume this. This meaning that a minus b, so we can also assume this. Then we realize that we should also assume that this is true. Okay. Yeah. and then we are done, right? So can any one of you summarize this proof and maybe say what is a little different or whatever is, if there is any, if you feel. Just try to summarize the proof. That will make it clear maybe. Because we're still just learning the technique, so it's not so much into the tactics. Just... Yes. Yes, so certainly that's the form. That's other forms of induction. They are nothing new. They can only prove from induction, but yes, certainly. Yeah. So you can always make this assumption that your statement is true from 1 up till k, and then prove it for k plus 1. Right? That is also okay. I mean, because see, roughly, logically, by common sense, it seems correct, right? That if you assume up till k and then prove for k plus 1, then it's fine. So we can just do that here. Or here we can just say that, you assume for k minus 1 and k minus 2, and then prove it for k. Okay. But when you say this, then there is an extra baggage that comes with it. Then in the base case, you have to show two things, two base cases. Obviously, in this problem, it is simple. We all know these two base cases. In fact, we wrote 3. But this is an important thing, right? When you are using 2 or 3 previous things, then if that's a fixed thing, right? If you are using 3 things, 3 previous things, then you do have to show 2 or 3 base cases. In the just logically you will see whatever you need according to that. Otherwise, it is not true. Okay, otherwise it may not be true. And yeah, so that's right. And the other version that you're talking, that we said, that you said, that Nagesh said, that can I assume that it is true for all k less than n? Yes. So in that case, what should be the base case? Let's try to think about that, right? In that case, what base case will we need? So let's remove this and think, because once you think about that clearly. So if the following holds, that S1 up till Sk, if the statements are true from 1 to k, then that implies Sk plus 1. So if we show this, then what else do we need to assume? Or rather, I should say, what should be the base case? Maybe that I should have written first, in a sense that asked first, just mentioned, what should be the base case, so that we can say, at least just by common sense, yeah, then we can say it's true by principle of strong induction. We can just quote it, but the first level we should understand is get comfortable. Later on, we can go into the logical details of these things. What can we say to say that Sk, or rather maybe let me just use some other Sn for all n. When I just write Sk or Sn, I mean Sk is true. What base case? Let's try to think about this. Do we need to have a more base case, or? Because it's clear that if you are using exactly 2 things from before, yeah, if you are using, so just like what we did in the previous question, right? See, if this thing is a little abstract, do tell me, okay, there is a merit to doing this, I'm doing this, but you should tell me if this is, yeah, if you are finding this. So let's say that if we are doing this, you see, look at this, then certainly you need S1 and S2 both, because using S1, you cannot even prove S2. Yeah. So this, if you do this kind of thing, which is the nature of induction in so many problems, then you will need to prove 2 base cases, and sometimes the second or third base case can be a little tricky. Okay, but in any case, I'm just, yeah. mean, just get comfortable with it and then just think freely and logically. Then you will get all the answers. Whatever I'm saying is nothing. Yeah. This all I'm trying to say is that just here is that if you are using two previous things, then obviously you need the base case to have two. Otherwise, as I said, you cannot prove S2. Then the base case should be S1 and S2. Then only overall. But you see, then can that be a base case if you have to prove till S capital? Yeah, but then you see, in fact, I'm just think, how do we prove S2? Can we prove S2? Let's obviously, I mean, obviously we need S1. Okay, but do we need to assume S2? Do we need to assume? So let's focus on the first part. Second is done. Do we need to assume S2? Satya, what do you think? Do we need to assume or do we need to prove S2 directly, or can we prove it from this first scheme that we have? No, so not the below thing, sorry. Sk plus 1. Yeah. So from this, can we prove S2 given S1? Yes, because this put k equal to 1, right? I mean, whatever surprisingly or not, but we don't need to assume S1, right? Because S1 implies S2. That is in the nature of the statement. Nagesh, do you see this? Right? And anything less than 2, if I know, then I know for 2. That's already in that. So the base case surprisingly here is just 1. Okay, but these are the subtle things. Maybe I'm trying to make it look more subtle than, but I'm not trying, but you can understand this is little bit is there. Okay, so you have to see. Okay. So here in this strong, this is called strong induction. Okay. You can obviously prove it from induction, but I'm not going into those kind of exercises because then it will take too long before we get into interesting problems. Today we did not do any much interesting problems. Okay, the utility one was nice, but okay. So this is the thing that in the strong induction, it's called a strong induction. You don't in fact need so then I mean, just wondering, right? Then why do we even need this kind of induction? This kind of induction? Yeah. Well, sometimes you will need it, right? Because the second one is independent of the first one. In some, like the last problem, right? Like the last problem, you cannot prove S2 independently. You will need to, I mean, you cannot prove S2 directly from S1. You will have to prove S2 independently, right? So for the last problem, in the case of S2, means A square minus B square, you could not have proved it from A minus B. So the first method, very logically speaking, does not apply. Right? At least for S2, it does not apply. But obviously, you can prove S1, S2, S3, and then you can apply that method. You can say you could use the first. But I'm just trying to say that sometimes there is a distinction. Yeah. Like if you need the last 3 statements or 4 statements, if you need the last 3-4 statements, then you have to put it in the base case. Then you cannot just say invoke the first one. You may think like, okay, the first one works, but then you will miss proving the first 2-3 cases. And then you will either prove a wrong statement or right statement in the wrong way. There is a subtle things. Once you prove these 3-4 statements, whatever is needed, first 3-4 statements, whatever is needed, depending, then you can invoke the first method, because then the first method gets going. The small things. Okay, so you have to be careful of that. Yeah. Yeah, so today I just stopped a little early. Okay, today I'm just stopping a little early on time. We have not done anything today. Mostly we just discussed this small subtle aspects, small aspects of induction, and we did one problem. Okay, next time I'll do a few more problems. So the book that I'm following here is Challenges and Thrills. Okay, so this is the book, standard book in India, Challenges and Thrills of Pre-College Mathematics. It's a standard book. It's a nice book. But obviously any book is fine. It doesn't matter to me. Yeah. So for today, I'm not giving any problems. Okay. For today, I'm not giving any problems. Next class I will give. Okay. Yeah. Let me just say that, or yeah, for today, let me not give any problems. Okay, you guys just see what you think about these things. If you just find time, just Google a little bit and see here and there. And obviously, if you have the book, then you can try problems on the book. So the first few problems, challenges and thrills, and from anywhere you just you can try problems. First few problems are like that only, like sum of squares of first and sum of cubes. And then there are some problems in Fibonacci. Nagesh, you may have seen this, right? This ones you have to try if you have the book. Yeah. And obviously, Satya, you can just, if you don't have the book, means any odd book you find online, mathematical induction, some problem sets, simple one. Let's try your first problems you would know. Or if you have the book, then it's fine. But obviously the chapter is there in intermediate counting and probability. So you can obviously, if you have that book, you can do it. But yeah, next time we'll do more interesting questions and then we will go forward. Okay. Yeah. About the next class. So this class, one day is already fixed.